Okay. There's a tremendous amount of applications to vectors, so please try to take these fundamentals to heart, try to get good at it with the assigned homework. So I gave you a very brief glimpse of vector algebra, and I showed you a really useful way to add vectors together just in the last example. So what I want to do now is continue on in the last few minutes today on using vectors and what you typically see in a math textbook, like our textbook. You should study, as I've said before, you should study the textbook. And a good way in college, I don't think I've said it before to you folks as a class, but oftentimes in college courses, try to take the time to read over the material before an instructor starts lecturing on the material. Even try the homework if you can, if it makes any sense whatsoever, before an instructor lectures on it. Then you walk into class and you'll be able to track a lot better. Okay? So if you have enough time in your life to do that, please do it. Now, when you open up a textbook, a trig book or an applied book that has vectors in it, you're going to see a lot of mathematics and a lot of rules there, and you should sort of study those sort of things. If you have vectors like A plus B, well, let's just say we have vectors A and B given to us. If you took 3 times vector A, think about the graphics I just did with you. You could break this vector up and write it as a component, AX and AY, times this value over here, 3. What would that do to the picture of A? What would this 3 do to the picture of A?
Stair steps.
Huh?
Like a stair step.
Okay, or what about the lengths? Yeah, wouldn't it just scale it up by a multiple of 3? Did you hear that word scale? This is called a scalar. A scalar value, a magnitude. And so all you're going to do with a vector is multiply it by 3. What if you tripled the wind speed? Doesn't the wind typically have a magnitude and a direction? And all of a sudden they say, oh, the wind speed tripled. Doesn't that magnify the components of both the x component and the y component? Right? So a scalar can distribute into the components of a vector. As an example here. Okay, so there's 3 times vector A. What would happen if I took negative of vector A? What would that do? What would that do to the vector?
Scale it down. It takes you in the opposite direction.
Does it scale it down in value? No, it just turns it around, doesn't it? Think about the picture. Point it in any direction you want. Let's say I point it this way. Here's vector A. What's a picture of minus vector A? Negative of vector A. It's going that way, right? Same magnitude, but in the opposite direction. Okay? So, what if I gave you this picture? Here's a picture of vector A. Here's a picture of vector B. And I ask you to find A plus B. No numbers given, just a scaled drawing. What would you do? Huh?
Put it at about 8 degrees.
What are you going to draw? What? I want a picture of this sum. What are you going to draw?
A single vector.
Okay, but you only know these 2. This is what's given. So how are you going to draw this? aren't you going to come up here and aren't you going to sketch vector A? And then do what with vector A? On the tip of it, hook on vector B, just like we did on our hiking trip. Make sense? And I'd put arrows on those things, because that shows the positive sense of them, doesn't it? And so where is vector A plus B? Where is this on this picture? It's a straight line from the starting point to the ending point. Make sense? Okay, we have a few more minutes left. What if, oh, here's something else. You're going to love this. Is that okay with people? In geometry, if I took these two vectors like we just did, and I set them up like this, what shape is that? What's that called? Parallelogram. Parallelogram. I've got something wrong there. My brain just had a lapse. Parallelogram. There. Okay. Got it? Opposite sides are parallel, different lengths. Okay? Where is the sum of these two vectors on that picture? Where's the sum of those two vectors on this picture? It's this diagonal right here, isn't it? From the starting point to the ending point. There's your A plus B. A plus B. What I'm interested in is what would happen if I asked for A minus B? How would you draw that? How would you draw that?
B positive A, negative B.
You'd come out here, there's your vector A, and you're going to hook onto vector A the opposite of B. Well, B was pointing this way, so I need a vector that goes that way. There's minus B, right? I'm adding those together, am I not? And so I end up with this vector. So this thing right here is A minus B. It doesn't have to be too complicated. You don't make it complicated. Just do what it asks you to do. But you have to understand each part. Vector A, magnitude and direction, and then the opposite of B added to it. Notice tip to tail. Tip to tail when you're adding vectors. Okay, so there's some algebra associated in some of your homework problems where they might say, find 3A minus B, something like that. And they might even give you components. Hang on for about 10 more seconds. I want to show you something else here just so that you'll feel comfortable with things. If we ended up with that last vector we had, vector R on the problem we did earlier, where we had 17.54 comma minus 1.14 miles. There's another way we found the angle, and we had our R value was 17.6 miles, and we had a theta value of negative 3.73 degrees. Okay, and we had associated picture of this. There's another way we could have written this vector. We could have written it this way: 17.6 outside, out in front. And inside, all I need are my unit circle cosine and sine readings of the standard angle associated with that vector. So all I need is cosine of negative 3.73 degrees, comma, sine of negative 3.73 degrees. Or I could have used 356.27 degrees there, or there. This is the same as that. And if you draw the picture, it should make sense to you. So the nice thing about representing a vector this way is all you need is the magnitude of the vector out in front and the cosine of the standard angle associated with it and the sine of the standard angle associated with it right there. It's a very nice way to write down a vector expression. Okay, that was a pretty quick thing. On Friday, tomorrow, we'll spend some more time on vectors, and then we have other topics that we'll get to in the following sessions. Okay, that's it for today.